So if you test positive for this super rare, terrifying disease, there is actually a really good chance that you're completely healthy, which sounds crazy, but today we're going to prove it to you.
Yeah, it is a mathematical reality that just completely breaks most people's brains, right? Mostly because um, human beings are just incredibly bad at intuitively understanding probability. Like we see a scary number and we just panic, and
Totally.
we completely miss all the invisible conditions that are actually shaping that number behind the scenes.
Right. Which brings us to today's deep dive. Welcome in, everyone. We are taking a subject that usually, induces a cold sweat for a lot of us statistics. And we're going to look at it not as some boring math requirement, but like as an actual survival tool.
Ex
It's basically the ultimate set of filters for navigating a world that is just constantly trying to manipulate you with numbers. And to do this, we're pulling from a really fantastic beginner's study guide. It's simply titled statisticsstudyguide.docs, and it's actually built on the courseware of JHS Peropin and the Alowski and Dean introductory statistics texts.
Yeah, really solid foundational stuff.
It is. So if you're listening to this to cram for a test, or honestly, just because you are so tired of being fooled by misleading headlines and like bizarre news charts, you are in the right place. We're skipping the dry chalkboard drone
Oh,
today,
goodness.
right? We are mining this guide strictly for the mechanics, like how data actually works, from collection all the way to outright deception.
Which is really the only way to build a true understanding. You have to trace the actual life cycle of a statistic. Because before anyone can use a number to predict the future or justify some crazy headline, they first have to categorize the messy, chaotic real world into neat little boxes.
Right.
And mathematically, that grouping starts with set theory.
Okay, set theory. Which, I mean, sounds like advanced theoretical physics or something. But the guide actually breaks it down into something super mundane. Like, a set is basically just a defined group of things, right?
That's all it is. Think of a set as just a defined boundary. Like you draw a circle, and everything inside that circle is an element of your set.
Okay.
So you could have a set of, I don't know, prime numbers or a set of blue cars or a set of people who drink coffee every morning.
Right, right.
And crucially, and this is a fun one, if you draw a circle and there is absolutely nothing inside it, that's called the empty set.
Oh, the empty set.
Yeah, which represents the total absence of elements. And that in itself is a really critical piece of data.
Okay, so where this gets really interesting and honestly highly practical is when you start looking at how those different boundaries interact with each other. The text uses a really great grounded example for this.
Yeah, the university campus one.
Exactly. So imagine a university campus. Set A is the boundary containing all the students studying math, and set B is the boundary containing all the students studying statistics.
Right, so we're picturing the classic Venn diagram here. You've got your two circles.
Two circles, right. And if you want to find the students who are dual majoring, like the ones studying both math and statistics, you look at that overlapping sliver right in the middle where the circles cross.
Exactly.
And the guide calls that the intersection. But if you wanted to send an email to anyone studying at least one of those subjects, you want the total contents of both circles combined, and that is called the union.
Yeah, and that distinction right there between both and at least one, I mean, it might seem like just semantics right now,
Right.
but it is the absolute bedrock of calculating probability later on.
Oh, totally.
But once you've defined your boundaries, you have to look at the actual elements inside those circles and ask, well, what kind of data are we actually dealing with here? Broadly speaking, the guide splits the world into qualitative and quantitative data.
Right. So qualitative is essentially just categories, right? Like hair colors, zip codes, blood types.
Yeah, exactly.
You can count how many people have O negative blood, but the blood type itself isn't like a number you can do math on. You can't multiply blonde by brunette.
Right. It just describes a quality, hence qualitative. Quantitative data, on the other hand, is numerical data, where the arithmetic functions actually represent reality, and the guide splits this even further into discrete and continuous data.
Okay, right.
So discrete deals with whole, indivisible units. You can count 5 cars in a parking lot, but you absolutely cannot have 5.2 cars.
Unless things have gone horribly wrong in that parking lot.
Exactly, yeah. But continuous data covers measurements where basically any fraction or decimal is theoretically possible, depending on how precise your measuring instrument is. So things like height, weight, time.
Okay, let's unpack this. Because once we establish we actually have numbers, the guide introduces something called the levels of measurement, which are nominal, ordinal, interval, and ratio, and the text is super strict about this.
Very strict.
It says the level of measurement completely dictates what kind of math you are legally allowed to do. So nominal is just naming things. But ordinal data is where we start ranking.
Right.
So ordinal data is like a 5-star rating system for a restaurant, right? 4 stars is better than 2 stars, but the actual like mathematical gap in quality between those stars isn't a fixed objective number.
Exactly. What's fascinating here is the crucial difference between those final two levels, interval and ratio data, because this is where human intuition routinely fails us.
Oh, really? How so?
Well, both of these levels deal with numbers where the gaps between the values are perfectly equal, right? Like the distance between 10 and 20 is exactly the same as between 30 and 40.
Yeah.
But ratio data possesses a true zero, while interval data does not.
Okay, wait. I want to make sure I grasp the practical difference of that true zero, because it sounds important.
It's massive. Let's apply it. So weight is a classic example of ratio data. 0 kilograms literally means the total physical absence of weight.
Right, it's just nothing.
Exactly. And because that true zero acts as an absolute anchor, you can do ratio math. So if you weigh 80 kilograms and your kid weighs 40 kilograms, you can definitively mathematically say you are twice as heavy as your child.
Oh, okay. Yeah, that feels completely natural to me. So where does it break down?
It breaks down with interval data, like measuring temperature in Celsius or Fahrenheit.
Oh, I see.
Yeah, because 0 degrees Celsius does not mean the total absence of heat. It's just an arbitrary point on a scale, the freezing point of water. Heat still exists below 0.
Right, right.
So because 0 isn't actually nothing, the ratio math is totally invalid. You cannot say that 40 degrees Celsius is twice as hot as 20 degrees Celsius. The physical energy does not double.
Oh, wow. So if I walk outside on a 40-degree day and I'm like, wow, it is twice as hot as yesterday, I am generating statistical nonsense.
Absolute nonsense.
Yeah.
Yeah, if you apply the wrong mathematical operation to the wrong level of measurement, the output is just fiction, no matter how precise that number looks on paper.
That is wild. And I feel like that perfectly transitions us to the next massive hurdle here. Because, okay, we categorize the world. We know what our data is in theory. But theoretical data is clean, right? Gathering it in the real world is an absolute mess.
Oh, it's a disaster. And this is the shift from descriptive statistics to inferential statistics.
Right.
Descriptive is safe. You're just summarizing the data you actually physically hold in your hand. Like if there are 30 people in a room, you can calculate their exact average age. There's no guessing involved.
But the thing is, nobody just wants to know about those 30 people in the room. They want to use those 30 people to guess the average age of the entire city. And that is inferential. You're making a leap.
You are. You're attempting to describe a larger, often completely unknowable population based on a much smaller sample. And the guide provides a brilliant, super simple memory trick for keeping the vocabulary straight here.
Yes, I wrote this down immediately when I read it. If you are calculating a number that describes the entire population, it is called a parameter. Both start with P. Parameter equals population. But because measuring an entire population is usually, completely impossible, we measure a smaller group, a sample. And the number that describes a sample is called a statistic. Both start with S. Statistic equals sample.
P to P, S to S.
Exactly.
S.
P to P, S to S.
It anchors the terminology beautifully. But, the entire field of inferential statistics hinges on one pretty terrifying question, which is, how did you actually choose that sample?
Right.
And the guide walks through several methods. So simple random sampling is literally pulling names from a hat. Everyone has an equal shot. Systematic sampling is picking, say, every 10th person on a list.
Okay, wait. Explain the mechanism of stratified sampling. The text emphasizes it pretty heavily, but how does it actually work in practice compared to just picking randomly?
Yeah, so stratified sampling prevents minority groups from being basically erased by random chance. So imagine you want to poll a university where 20% of the students are international. A purely random sample might accidentally pick only domestic students, just by chance. So with stratified sampling, you actively divide the population into those groups, or strata first.
Ah, I see.
And then you randomly sample within those specific groups in proportion to their actual size. So it forces representation. It ensures the international students make up exactly 20% of your sample.
Okay, that makes total sense for building a fair sample. But looking at the final method the guide lists, convenience sampling.
Oh boy.
The definition is literally using results that are readily available.
Wait, isn't that just every social media poll or like a person with a clipboard standing outside a single grocery store on a Tuesday afternoon?
That is exactly what it is. And the text explicitly warns that convenience sampling is highly biased and basically the worst method statistically.
Because if you only poll your own followers, or I don't know, only people who shop at high-end organic markets at 2 in the afternoon, you are gathering data from a highly specific, fundamentally skewed echo chamber. Doesn't that mean we are surrounded by terrible statistics? Yes. Yes, we are. If we connect this to the bigger picture, it brings up a really vital distinction: sampling error versus non-sampling error.
Okay, lay it on me.
So sampling error is the natural, unavoidable variance that occurs just because you didn't measure every single person on Earth. It's a mathematical reality.
Right.
And you can shrink it by just gathering a larger sample, right?
Yeah.
Asking 10,000 people instead of 100 people reduces your sampling error.
But let me guess, gathering more data does not fix a convenient sample.
Not even slightly.
Ew.
Because that is non-sampling error. Those are human mistakes. Biased survey designs, leading questions, data entry typos, or, using a flawed method like convenience sampling.
Right.
If your fundamental method is biased toward a specific demographic, serving 1 million people instead of 100 people just gives you 1 million highly biased answers.
Wow.
Yeah, no amount of data fixes a non-sampling error. It literally just amplifies the lie.
That is a deeply chilling thought when you consider how much of our daily news is driven by convenient social media polling. But, okay, let's assume the best. Let's assume we used rigorous stratified sampling, we completely avoided non-sampling errors, and we have clean, honest data.
A miracle.
A total miracle. Now, someone has to publish it, right? They have to visualize it for the public. And the guides section on visualization reveals that charts can be just as manipulative as bad sampling.
Oh, absolutely. A visual chart bypasses our analytical brain and speaks directly to our spatial perception. It is incredibly easy to exploit that.
The guide covers the standard toolbox, right? Bar charts for distinct categories, histograms for continuous data where the bars touch to show flow, line graphs for time trends, scatter plots for seeing if two variables correlate.
Standard stuff.
But here's where it gets really interesting. The text features rules from statistician Carl Bruman on how to display data badly, which is amazing. It reads like a list of cardinal sins for data scientists.
There really are practices that actively distort reality.
The ones that stood out to me: never use 3D charts and never start a y-axis above 0. And the thing is, I see both of those constantly in corporate presentations and news broadcasts. Why are they considered so mathematically offensive?
Because they literally weaponize human biology against the viewer. Let's take the 3D chart, right?
Okay.
Adding a fake third dimension to a flat screen forces the software to tilt the image, which plays with perspective. The bars in the front visually take up more pixels on the screen and look vastly larger than the bars in the back, even if the actual data values are identical. It tricks your visual cortex.
That is sneaky. And what about starting the y-axis at, say, 50 instead of 0?
Oh, that is the oldest trick in the book for exaggerating a trend. Think about it. If company profits go from 51 million to 52 million, that's a pretty tiny incremental bump.
Right, bare minimum growth.
Exactly. And if you start the y-axis at 0, the line looks basically flat. But if you start the y-axis at 50, that $1 million difference suddenly looks like a massive vertical rocket ship taking off. You are visually lying with perfectly accurate numbers.
Okay, the text also harbors this deep, almost visceral hatred for pie charts, which kind of surprised me. Why the hostility toward the pie? I love a pie chart.
Again, it comes down to human perception. We are biologically quite good at comparing the lengths of straight lines, which is why bar charts work so well.
Okay.
But we are terribly inaccurate at comparing angles in two-dimensional areas, which is exactly what a pie chart requires. If you have a pie chart with 6 slices that are roughly similar in size, the human eye just cannot rank them accurately.
Wow. The text actually suggests that sometimes the most revolutionary visual you can use is just a boring black and white table of numbers. Why would a boring table ever be better than a chart?
That points to the golden rule of data visualization. A chart exists to answer one clear question. If the viewer has to squint, read a complex legend, and physically mentally calculate areas to understand your point, the chart has failed. Clutter distracts from the truth. So often, a cleanly formatted table is vastly superior to a noisy, over-designed graph.
Okay, so we've tracked the life cycle of this data. We defined the boundaries, we gathered the sample, and hopefully we displayed it without using a 3D pie chart.
Hopefully.
But up to this point, we have only been describing the present. The guide shifts gears pretty significantly in Unit 3. We move from describing what is to predicting what will be. probability.
Right. This is the mathematical framework for uncertainty. Probability is simply a numerical measure of how likely an event is to occur.
And the foundational rules here govern literally everything that follows. Rule 1. Probability is always expressed as a number between 0 and 1. 0 means it's a physical impossibility. 1 means it is an absolute certainty.
Yes.
And Rule 2. In any given scenario, the sum of all possible probabilities must equal exactly 1.
Perfect. From there, we need tools to calculate multiple events. The guide starts with the addition rule, which is what you use when you want to know the probability of event A or R event B happening.
Okay, I want to walk through the text-specific example here because the formula has a sort of trap door in it. The example uses a standard deck of 52 playing cards.
Classic.
Let's say you want to know your odds of drawing either a red card or a king.
Right. So the intuitive but incorrect approach is simply adding them up. You know there are 26 red cards in the deck, 26 out of 52.
Right.
And you know there are 4 kings in the deck,
Yeah.
4 out of 52. If you add 26 and 4, you get 30 out of 52.
But the formula states you have to subtract the probability of A and B happening together, so why are we subtracting anything?
To avoid double counting, look really closely at those 4 kings you just counted. 2 of them are black, but 2 of them, the king of hearts and the king of diamonds, are red. Yeah. When you counted the 26 red cards, you already counted those 2 red kings. When you counted the 4 kings, you counted them a second time.
Yeah. So the overlap inflates the answer. We subtract the 2 overlapping red kings, so they are only counted once. So it's 26 plus 4 minus 2, which gives us the true probability 28 out of 52.
Precisely. The only time you skip that subtraction is if the events are mutually exclusive, meaning they physically cannot happen simultaneously.
Right.
Like drawing a card that is both a spade and a heart, that's impossible, so there's no overlap to subtract.
So that handles the or-are scenarios. But what if we want to know the probability of multiple events happening in sequence? Event A and D event B, like drawing a card and then drawing another card.
That requires the multiplication rule, which introduces one of the most important concepts in all of statistics, the difference between independent and dependent events.
Okay, the guide uses coin flips and card draws here. Let me see if I can propose an analogy for the mechanics.
Go for it.
So, flipping a coin twice is an independent event. A coin is like a goldfish, right? It has absolutely no memory.
I like that.
When you flip it the second time, the coin does not know or care that the first flip was heads. The physical universe hasn't changed at all, so the odds are always 50-50. You just multiply 0.5 by 0.5 to get a 25% chance of 2 heads.
That is a solid analogy. The goldfish basically resets every time. But now compare that to drawing 2 aces from a deck of cards without putting the first card back. Right. That is a dependent event.
So if flipping a coin twice is independent because the coin doesn't remember the first flip, drawing 2 aces without replacing them is dependent because the physical deck has actually changed.
Yes. You alter what statisticians call the sample space, which is the total universe of possible outcomes. When you reach for that first card, your sample space is 52 cards, and 4 of them are aces. Yep. But if you pull an ace and keep it in your hand, your universe physically shrinks. When you reach for the second card, your sample space is only 51 cards, and only 3 aces remain. So the mathematical reality of the second event is entirely dependent on the outcome of the first event.
Recognizing whether an event is a goldfish or like a shifting ecosystem seems super vital. And that concept of the shifting ecosystem, the first event changing the math of the second, leads directly to the climax of the study guide.
It does.
Because probability isn't just, parlor tricks with cards and coins. It governs medicine, law, survival. We are talking about conditional probability.
This is the math of context. We are no longer asking what is the probability of event A. We are now asking what is the probability of event A given that event B has already happened.
This brings us all the way back to the hook of this deep dive, the medical test paradox. The text explains Bayes' theorem, which proves that testing positive for a rare disease does not mean you definitely have it.
It is wildly counterintuitive. When people see a positive test result, they immediately assume it is a certainty. But the test result is really just a condition. To find the true probability that you are sick, you have to weigh that positive result against the false positive rate of the machine and, most importantly, how rare the disease actually is in the overall population.
Right.
If the disease only affects 1 in a million people, a positive result from a test with a 5% error rate is far, far more likely to be a false alarm than a true diagnosis.
Okay, the guide offers a visual tool to help process this kind of shifting condition called a contingency table. Let's take this slowly because visualizing this really unlocked the whole concept for me.
It's a great tool.
Picture a room with exactly 100 people in it, and we are tracking two variables, whether they smoke and whether they are sick.
Okay, 100 people. Let's establish the borders of our groups here. Out of the 100, let's say 70 are smokers, leaving 30 non-smokers. And looking at health, out of the same 100 people, 50 are sick and 50 are healthy.
Right. And the crucial piece of data is the intersection in the middle. Let's say 40 of those people are both smokers and sick. Now, watch how conditional probability completely changes the narrative depending on how you ask the question. Let's ask, what is the probability that someone is sick given that they are a smoker?
Ah, see, the word given changes your entire sample space. You are no longer looking at the room of 100 people. You only look at the 70 smokers.
The universe shrinks.
Exactly. Out of those 70 people, 40 are sick. 40 divided by 70 is roughly 57%.
Okay, so if you are a smoker in this room, there is a 57% chance you are sick. Now, flip the condition. What is the probability that someone is a smoker given that they are sick?
Again, the sample space shifts. We completely ignore the smokers and focus strictly on the 50 sick people. Out of those 50 sick individuals, 40 of them are smokers. 40 divided by 50 is 80%.
That is staggering to me. 57% of the smokers are sick, but 80% of the sick people are smokers. The numbers swap places completely based entirely on the invisible condition you applied to the question.
This raises an important question, though, right? How often do we misjudge risk in our everyday lives because we simply don't understand conditional probability?
All the time, probably.
Knowing the difference between the probability of being sick if you're a smoker versus the probability of being a smoker if you're sick, it's a profound shift in critical thinking. When a headline screams, "Most car accidents happen within 5 miles of home," people immediately panic and think their driveway is the most dangerous place on earth.
Oh, I've seen that one.
Right, but they miss the condition. The condition is that you spend 95% of your driving life within 5 miles of your home. It's not a dangerous zone. It is simply where your sample space is the largest.
It's a total paradigm shift. I love that.
Yeah.
Before we wrap up, I want to highlight one last brilliant shortcut from the guide. They call it the at least one trick.
Calculating the complement. It is incredibly elegant.
So what does this all mean? Well, imagine you're flipping a coin 3 times, right? And you want to know the probability of getting at least one head. If you do it the long way, you have to calculate the odds of getting exactly one head, plus the odds of exactly 2, plus the odds of getting all 3, and then add them all up.
Which is tedious and leaves room for error.
Very tedious.
Yeah.
But the guide reveals this massive mathematical shortcut. The probability of getting at least 1 equals 1 minus the probability of getting none at all.
It perfectly utilizes that fundamental rule we mentioned earlier. All probabilities in a scenario must add up to 1.
Exactly. So instead of doing all that complex math, I just figure out the odds of getting 0 heads, which just means rolling 3 tails in a row. So a 50% chance times 50% times 50% equals a 12.5% chance of getting all tails. Then I just subtract that 12.5% from 100%, and the answer is 87.5%. You calculate the probability of something not happening to instantly find the probability that it will happen.
It saves immense amounts of time and drastically reduces your surface area for arithmetic errors.
Yeah.
It's really just a beautiful piece of logic.
It really is. Well, we have covered a massive amount of conceptual ground today. We tracked the entire life cycle of data. We started by drawing boundaries with set theory just to see what data actually is. We established why knowing the difference between interval and ratio levels of measurement prevents, mathematical disasters.
Very important.
We waded into the messy real world of inferential sampling, defining the trap of convenience samples and non-sampling human error. We looked at how charts manipulate our actual biology. And finally, we learned how conditional probability dictates the true risk of the events all around us.
It is a truly formidable toolkit for anyone to have. But, considering all the mechanisms we've unpacked today, from the unavoidable mathematical reality of sampling error to the easily weaponized visual distortion of a y-axis, I really want to leave you with a final thought to process on your own.
Let's hear it.
When you scroll through your news feed tomorrow, look at all the supposedly objective data-driven articles and charts. How much of what you are seeing is actually empirical truth, and how much is just a carefully constructed statistical illusion? If natural sampling error is unavoidable and human non-sampling error is everywhere, next time a chart makes you feel angry or afraid, just pause. Ask yourself, what is the sampling error they aren't showing me?
Wow. Those are the exact questions you need to dismantle the illusions. Keep looking for the hidden overlaps, definitely question the sample space, and whatever you do, never trust a 3D pie chart. Thanks for taking this deep dive with us. We will see you on the next one.